Welcome everyone to a NAC webinar, another edition of the NAC webinar series. We have today the title of our presentation will be Shape-Changing Micromachines by Dr. Daniel Lopez from right here at Penn State University. I'll do a more a longer or more extended introduction in a couple of minutes here. So I just want to remind you that this webinar is hosted by our center here at Penn State, which is an NSF ATE, which is Advanced Technological Education Regional Center for Nano Fabrication Manufacturing Education, where it's called the NAC Center, or Nanotechnology Application and Career Knowledge Resource Center. We thank the NSF ATE for making this webinar possible to all of you across the country and around the world. We are actually housed here at the Center for Nanotechnology Education and Utilization, which is in the Engineering, Science, and Mechanics department here in the Penn State College of Engineering. The webinar is being recorded. The link will be available at our CNEU site and as well as our Nano4Me site. And probably it depends on when things render and so on, but the last webinar took about a week to render. We will put it up, make it available whenever we have it available and probably early next week it will be available for your use. Again, use the Q&A module. We appreciate that. We will look through the chat also. So feel free to use the chat for chatting with one another or chatting with us if you have questions or would like to make any comments. Our co-hosts today are myself. Again, my name is Bob Ehrman. I'm the managing director here at that NAC Center that I talked about earlier at Penn State. Mike, would you like to introduce yourself too for a second?
Thank you, Bob. I'm Mike Lasecki. I have a long-standing relationship with the micro nanotechnology community here at Penn State, and also I act as co-PI for the project called Preparing Technicians for the Future of Work, and it's my pleasure to be here today. Thank you, Bob.
And Mike, how long have you been involved with NSF ATE?
I was fortunate to have one of the early centers in semiconductor manufacturing technology. It launched in 1996.
Fantastic. So he's been around a year or two. We call him our rookie member of our team here.
Thank you.
And I'm pleased to actually introduce Dr. Lopez, Dr. Daniel Lopez. Daniel, you're here at Penn State. You're a Liang professor at VE, Electrical Engineering. You're the director, also recently appointed the director of our NanoFab or Nanofabrication Laboratory at the MRI or Materials Research Institute. Is that correct, Dr. Lopez?
Yes, that's correct. I'm new here in the area, and so far I'm enjoying it. It's a great.
You're enjoying the April snowstorms? Is that what you're telling me?
Yes, this morning was a big surprise.
So, Dr. Lopez, you're not from the United States originally. Is that correct? Where are you from, and where were you educated?
I was born in Argentina. From there, I'm a physicist. I was trained as a physicist. I did my PhD there in a nice place in Patagonia. The city is called Bariloche. It's a very a well-known center for low-temperature physics there. And from there, I moved here to the US, as you know, to IBM, and I work in different places before moving to Penn State.
You worked at IBM in upstate New York, correct? Or the upstate is just north of New York City.
Correct. Yes,
anything
yes.
North of New York City is upstate, actually, right?
In Yorktown Heights, yes.
Fantastic. And then you moved to the Garden State, from what I understand. You moved to Bell Labs.
That's true, to a beautiful place called Bell Labs. At that time, Bell Labs is a well-known organization across the world. Because it was critical for a lot of the advancement in basic and applied research in the US. The organization still exists, but the mission is a little bit different than it had in previous year. But yes, after IBM, I moved there, where I basically got involved with nanotechnology there for communications at that time.
Great, and you received the President's Gold Award there. Congratulations. That sounds fantastic. And then in 2008, you moved to, I guess you moved to Chicago. Is that correct? The Chicago area?
Yes, I lived there for more than 10 years. I mean, basically after Bell Labs, at that time, the company handling Bell Labs was Lucent Technologies. Then Alcatel bought the company, and again, the mission and vision of the company drastically changed. And I moved there with another people from Bell also to Argonne National Lab, which is very close to Chicago, which is a beautiful city, cold in winter, but a beautiful city.
And you also did some work at, I guess, the University of Chicago. Is that correct too?
Yes, I was affiliated with them also.
Fantastic, fantastic. And you're also, right, presently, in addition to your work at Penn State, from what I understand, you're also at NIST to do some work with NIST, or is that correct? National Institute for Standards and Technologies. Yeah,
that's correct. And plan of this, some of the activities that we are doing here at Penn are being done in collaboration with NIST, which is a spectacular federal facility for research in quantum activities and things like that.
Fantastic. Now, I'm going to just give you a couple more tidbits of information about Dr. Lopez before he begins his presentation. His careers cover many areas, such as novel materials, micromechanics, optical microsystems, and nanofabrication. Common theme has been using the interplay among mechanics, photonics, and materials to advance fundamental and applied science. Some recent notable examples of his research include the fabrication of today's fastest and densest spatial light modulators, the development of methods to improve the performance of oscillators using nonlinear resonators, the most precise characterization of quantum mechanical Casimir interaction, and the development of optical nanosystems incorporating metasurfaces and MEMS devices. I said that especially for one of our people on our audience, Dr. Matt Plyle from the University of New Mexico. I have to say MEMS 3 times every hour just to satisfy him. He has authored more than 150 technical publications, holds more than 30 granted and pending patents, and has given invited talks worldwide. He collaborates with industrial sector and with researchers and educators globally. And we're very happy to have you, Dr. Lopez, and I'm going to stop sharing and turn over the rostrum to you, sir.
Okay. Thank you, Bob. Thank you, Mike. Thank you, Rene. I'm glad for this opportunity that gave me a good excuse to get to know the NAC Center. And I'm happy to be able to present here the work that I've been doing in past years and what we are planning to do from now on. No? And I'm looking forward to potential collaborations together, because the field of nanotechnology apparently is a never-ending one. No? But please interrupt or send text. I mean, I'll be checking. I have the chat is open there, but let me know if you have any question, and you're welcome to contact me after the talk if you want. This is my email. Let me go to the laser pointer. This is my email, and that's the best way to reach me. What I'm going to show you today is a very high-level description of the field of miniature micro machines, and the field is starting to take off today in a variety of areas, and perhaps the ones that one of the pioneers in pushing the field was Richard Feynman. You guys are, I'm sure most of you are well familiar with. He's the one who proposed, for a lot of people, is the father of the field of nanoscience and nanotechnology. And he proposed 3 things when you start reading what was his main ideas. One was to miniaturize information and miniaturize computation science, computing in particular. These 2, almost everybody is very familiar with that. Nobody will question how significant has been electronics for humankind. Where are we now? The kind of thing that allow us to manipulate information. We can talk for hours about that. But he also talked that will be very, very useful to create miniature machines. And miniature machines are basically, from that point of view, and I'm showing you some of the examples today, this is a very primitive field, but it's starting to grow really fast now, is is basically a very general concept. No? We're talking of anything, any machine or any device that can gather information and manipulate environments and the micro and nano world. Basically, this will be spectacular devices to interact with the micro and nano world to do a lot of things. Let me show you what people has been doing in the past 20 years in that direction. And what I'm showing here today is some representative pictures of my previous work in the field of micro electromechanical systems, or MEMS, that has been very popular. It's already a well-developed technology. It's a very mature technology. You can see here, these are some devices that were fabricated for optical communications. I'll show you briefly later how this works. These are also MEMS, micromachines to manipulate light to create tools that can go inside the human body. This is a microphone. The dimensions, you can see the scale here is of the order of 0.5 millimeter, 500 microns. This is a device to measure magnetic properties of elements. But one thing in common here is the dimensions of these devices are of the order of hundreds of microns. Most of these devices are fabricated with silicon. Silicon is a beautiful material. It's well understood. People have been working in this material for decades. And one important thing for this material is silicon is an elastic material. Basically, you can, if you have a spring like this one, you can stretch it, you can deform it several times its typical size. And if the material recover, if you do not break the material, it will recover to the initial shape. It's very useful for men, has been very well characterized. You can see here some springs that have been that they are under torsion, but basically this is one of the main features of these materials. You can deform them, and if you do it right, they won't break. And if they don't break, they will return back to the initial shape. But as I said, this technology is well understood. I'm not saying it's easy to fabricate these devices, but people know precisely how to make them, how to control the properties of the materials, how to integrate them with electronics, and they are literally present in a variety of things that sometimes you don't even realize how important they are. One important application that we developed in the past years, this was done at Bell Lab, is to use these MEMS devices, these little mirrors. These are mirrors that can rotate, as I was showing you in the slide before, along two axes. They have one axis here that allows torsion along this axis, and this axis is supported on top of this outer gimbal that can rotate in a direction perpendicular to this one. In that sense, you can have this two-dimensional rotation, and when you shine light on these mirrors, just by rotating them, you can reflect the light and send it to any way you want. In particular, this was very useful to use light for internet. This is used today in quite a few places. The light coming out from one optical fiber could be the light coming from your office. And basically that's the signal that you want to send to another website. And just by changing the angle, you reflect the light to another fiber. And you can do that very, very fast in the optical domain without changing the light in electricity, working in the electrical domain, and then going back to the optical area. That is slow, and that is a bottleneck for communications in particular. But this technology is just one example of the thing that people has been doing with MEMS. This was perhaps the biggest applications of MEMS when they started to be popular, and they can handle the humongous amount of data that you use in an internet minute today, and this cartoon show. But again, this is one of the examples of these MEMS. As you can see, these are mirrors of hundreds of microns in size. You see the dimension like a 500 micron. This is 0.5 millimeter, and they are far apart. You see there is a lot of space in between these mirrors for different reasons that is not utilized. No? This is one example. As I said, MEMS are everywhere today. In a typical cell phone, in a typical smartphone, you give basically, you have included there probably of the order of 14, 20 MEMS today. You can measure, as you know, position, you have timing capabilities, you have speakers, you have microphones. There are a lot of interesting things that I'm going to show later during the talk. In cars today, also is impressive. Perhaps the most popular application is the capacitive sensor that goes in a car to trigger the airbags. When the acceleration changes really bad because you have an accident, the airbag will deploy. And this is literally controlled by a little device who costs a fraction of $1 today because can be fabricated with the technology used to fabricate integrated circuits. But this is one example. You see tire pressure monitor, a lot of things, GPS, a lot of things are literally based on MEMS. And there is a great future related to Internet of Things. Remember, we want to put basically every object that we interact on a daily basis, we would like to connect it to the web, to the internet, to manipulate or to get informed about what's going to happen about that. No, that's basically the present and where this is going. But as I said before, it's a technology well known. We know how to fabricate these devices and we know how to actuate these devices. The method to fabricate it is, there are several, to actuate them, sorry, there are several of them, but the most popular is applying electrostatic forces. And that is literally not a new technology, it's literally an old technology based on similar what Coulomb used in the 1800 to basically to measure the charge of electrons, for example, to study the electrostatic forces. And this little cartoon that you see here is one of the actuators that we do. Well, basically the way we work is we apply a voltage to this structure from the outer world. This force will deform the material, and when I turn the voltage or the force off, when I apply the force, I turn the force off, sorry, the deformation will disappear and the material will move ahead. This is known as a scratch drive, and it's popular in some applications, perhaps not the most popular, but it's useful in several things. I mean, this is what you can see here is a movie of a real device that we fabricated. Each little structure that you see here is one of these scratch drives seen from above. You see what we are doing here is applying a voltage, and what we are doing is turning the applied voltage on and off, basically. And that's what we are making is this structure to scratch and move around the surface. You see, if you have one, you can make many of them. All of these are pushing together. You can see that they are moving one spring here. And as you will see in a minute, they can move really fast, no? And you can see there when you can see the external probe, and you can see that again. I don't know if I said, but the sizes of these devices of the order of 50 microns, something like that. Not too big, but reasonable size for the mic. And you can see they can move really fast. You see some of them sometimes cannot follow, and that's what makes your life miserable when you work with these devices. You see these three are trying to go away, but they are not going to make it too far. But this is, you see, I want to show you a catastrophic event. But the important thing here is, in this world, you balance your electrostatic forces with mechanical deformation. And that's how you induce motion. And one of the things that you can do is to push things out of the plane. Now, remember, I showed you before this little tent. This is a microphone. This is a plate that allows the wave, the sound to go through, and then you measure that in a specific way. But the way these devices are fabricated is you make them flat, and then you need to pop it up. You need to push it in a way that the device will go out of the plane in order to be a better microphone in the microscopic domain. No? These are hinges that you can fabricate with polysilicon, and this structure that I showed you before are shown for that kind of thing. You see, again, these are the little actuators that I show, and what we are doing, I'll play this twice, don't worry, is just we will push together, they will start pushing together this flat structure, and you will see how it pop up. You see now it's moving, they are pushing from this side, and you can see here in this cartoon, there is the microphone flat, and now it's coming out of the plane. It's getting dark because it's reflecting the light away. But you can see how they are pushing literally and helping to move structures that are created flat to make them 3D. You see, let me just show you again, just because this is a useful example. These are these scratch drive. You start applying your voltage, they will start moving, and they will start pushing laterally to this little tent that will literally jump out of the plate because it's supported by these hinges. You can see how they move. These are fabricated devices. This is well understood. And you see how this initially flat structure ended up being a three-dimensional structure. No? The novelty here is that micro machines can be used to build another micro machines. And that is something that is pointing to something bigger than what the technology has achieved, and is useful for what we are discussing in the next slide. But this gives you a big description of what is the world today of this MEMS technology. You know, it's just hundreds of micrometer-sized devices that they can move. They can do very interesting things. It's a really well understood technology with a lot of successful commercial applications, with a lot of potential also for the future. But what I'm going to show you in this talk is where is this field is going. And there are two big areas of the field of micro machines. One is to put a lot of them together, to make them very small and put them together. I'll show you why. Basically, you want to go from micro to nano machine. And the other is to make them a little bit more intelligent than they are today. You see, all the machines, all the examples that I show you today are microscopic machines that you manipulate from outside. You see, you need to apply the forces, you need to control what they do, you need to look how they behave in order to correct or improve the performance, but basically you are in charge of controlling them. One of the areas where this technology is trying to go, and I will talk most of the talk about this, is basically created systems with some degree of intelligence inside them, and we'll see how to do it. Again, let's go first to this one. Let's see these two evolution paths. Remember, one of the areas is, as I said, is to do very large scale integration of micro machines. The idea is very similar to what happened in electronics with the transistor. As you know, this is the very famous picture of one transistor that was developed at Bell Labs in 1950, around that. If you have few transistors, you can make a radio. If you have few millions, you have a Pentium, which is an old thing today. And you have today, this is a state of the art. You see, if you can put 40 billions of transistors in a chip, you have a high-end microprocessor, and you guys know what you can do with a state-of-the-art microprocessor. This is one path of what Feynman suggested some time ago. This is a beautiful example of exploring and pushing a technology toward the limits, and all the things that you can do with this technology, manipulating information, and it's really well understood. MEMS are trying to do something similar. You see, this is the example I show you. Was a big mirror, hundreds of microns, a lot of space between them, that you need that space to manipulate this device, but the technology has been moving forward in a path similar to the field of transistor. The goal is to put many of them in a chip, because in principle you will not waste any space on the chip. And in particular, the farther you push it down to the size, to the nanoscale, the better, the more possibilities to do different things that you are doing. You see, one of the big directions for the future of the field of micromachining is this one, is building the mechanical equivalent of a Pentium chip. You see, now if you have billions of transistors, you can have millions of MEMS devices that are giving you arms to your microprocessor. You can do a lot of things that today you can't. Just to show you one example, very briefly, to finish with this field, with this area, this is some of the things that we are doing. If you could have a lot of these mirrors, remember, I show you a big mirror to manipulate light for communications. If you can reduce the size of those mirrors from hundreds of microns to few microns, there are a lot of things that you can do. And these are some of the programs that we are developing right now. For example, you can create small chips that you can implant on the brain. And that chip will manipulate the light that you control from outside and will illuminate predetermined populations of neurons to control or to trigger or to measure some response. This belongs to a bigger field than that, is the field of optogenetics, but the idea is to control the brain, to interface with the brain, with human brain or animal's brain, using light. This is very interesting. And it's at the very beginning, people is not even close to get here, but this is something that is really, really propagated. The same large arrays of mirror can be used to manipulate the quantum state of atoms, and that is key to make a quantum computer that can be practically useful. But again, it's complicated to make for reasons that we will discuss later, but this is basically a very, very big deal today. And we are interacting with companies like Texas Instruments for something more practical application on a daily basis, which is to use this array of little mirrors for what is called adaptive laser headlights. The idea is you put these MEMS, these little mirrors in your car, and you can manipulate the shape of the light that your headlights are projecting. Then you can have situations like that where you control where you do not want light to avoid disturbing, for example, a driver coming toward you, or you can eventually project some patterns on the pavement to communicate with pedestrians, for example. At the core of this thing are little mirrors like this little piece of silicon that I'm showing to you here. These are some springs that we can talk later. But the sizes of these mirrors are now 3 by 3 microns. Remember, what I showed you before were 300 microns. Now we're 2 orders of magnitude, even less, in smaller devices. We are moving from the micron world to the nano world. And in particular, the springs, the features that you need to include there to control the performance have dimension of the order of 100 nanometer, another order magnitude smaller. And we are really getting into the field of NEMS, which is nano electromechanical system. And I see that one of the comments there is about the digital multimeter devices from Texas Instruments. This is the next evolution of these devices. That's a very good comment. Thank you. If you want to compare this with the devices from Texas Instruments, the ones from Texas Instruments are mirrors that are on-off, basically. They are flat and they reflect the light, and you tilt them away and the light is off. This is much more complicated because what you want to do is to control the intensity of the light continuously. You don't want to have an on-off device. You need to control the intensity of light almost continuously between bright and dark. And that can be done only with this technology that doesn't exist today for a variety of problems that we can discuss in more detail next time. No? But I'm showing you what happened when you are trying to go from MEMS to NEMS. And one of the issues is when you get to these dimensions, this sub-micron, there are a lot of physical problems, a lot of issues that when you deal with 100 micrometer devices, you don't need to pay attention, but now they are really becoming a big issue. One of the problems with the MEMS devices, when you reduce the size, is that you do not have a Moore's law. Why? And this is an interesting point for all the students here to think about. No? I mean, for example, the transistor is called a scale invariant. This means that if you make a transistor humongous, this big, the physics, the fundamental principles behind the working of the device are independent of the size of your device. You can make it 1 micrometer big or 10 nanometers small, and the physics behind the performance is exactly the same. That is called a scale invariant, and that allows you to do a Moore's law. And that is very important for the companies because the companies know that they can invest billions of dollars to fabricate these devices, and you know that the device will work. I'm not saying it's trivial, nothing is trivial, but the physics behind that is not changed. With Micromachine, that doesn't work because the physics change when you change the scale. If you go from hundreds of microns to nanometers or sub-microns, the physics changes. You need to take into account parameters that parameter phenomena that you didn't take into account before. And that has been a big limitation to scale down MEMS to NEMS. And this is one of the big areas in the field today, is to try to understand the phenomena that you face when you reduce the size of these devices. This is a 3-slide description of one of the areas where this thing is going. We are moving from hundreds of microns and far apart devices to literally few microns or sub-micron structures very, very close to each other. And that triggers a lot of issues that we can chat next time that we meet. What I'm going to show you now is the second big direction, which is to create intelligent microsystems. As I said before, all of these devices require extreme control from outside. What we want to do now is to see if we can create devices with some level of intelligence that they can make decisions without us getting involved there. But before that, let me know if there is any question. The organizers asked me to do this, and I'm curious to see if, before we move away from this particular area, if you have any question.
Dr. Lopez, it's Mike. I'm going to jump in with a question from our colleagues. That mirror array that you talked about, is the basis of that, is it one of the grating light valve devices? Is it similar? What's the basis behind that?
Good question. The way this function is the same. Suppose that you have millions of these very little mirrors.
Yes.
All the mirrors, let's assume, just to simplify, that these mirrors can move up and down. This is different to the DMD from Texas Syndrome. Suppose that all the mirrors are at the same height, and you illuminate, for example, basically what you have is a bigger mirror. You send light, you illuminate, the light will be reflected. If you move one of these little mirrors down, if you move it the right amount, the light reflected from that mirror could be out of phase, it's called like that, with the light reflected from the rest of the mirror. Then the light reflected by that little mirror will interact with the rest of the light in a destructive way and will create a black spot, a dark spot. Then if you now move the mirrors up and down independently, you can create different black or dark spots. If you move them less than the optimal amount, instead of having a black spot, you will have a gray spot. And then you can control the intensity of the light that cannot be done with the standard MEMS technology commercially available today. But this is the big explanation. You have this large array of mirrors. Each one should be able to move continuously up and down. It's not an on and off device. It's a digital device that has to have different bits for control. Each mirror can move almost continuously as a piston motion, and that allows you to project images very, very fast with a lot of control on the intensity of the lights there.
Okay, perfect. You know, we have one other question, and of course we're fascinated by this idea of going towards NEMS, but what physical properties, as you design or implement them, for example, is it harder to do temperature compensation, or you know, briefly, what kind of parameters do you need to consider as you move down to those really smaller nano dimensions for MEMS?
Okay, yes. Just one question to Matthias there. I go to your question in a second, Mike. Yes, Silicon Light Machine did something similar for dimensions much, much larger. And Silicon Light Machine created a one-dimensional array of mirrors. One-dimensional array means that you have one mirror here, one to the left, one to the right, one to the left, one to the right. And basically that is a very easy way to do it because you can put all the electronics outside your movable part. This is a 2D array. You need to the array for this application. And the problem is the only space that you have here to put the controlling electronics is below under each meter. And as I said before, each meter is 3 by 3 microns. If you go and you ask people how much current, how much electronic, how much voltage I can get in that area, they will tell you 2 volts if you're lucky. And with 2 volts, you don't have a lot of forces to apply. And that makes your life much more complicated. That's why you need very small springs and things like that. And that has been a challenge in the field. And I'm now connected to your question, Mike. What are the problems? I wasn't very clear there, but for example, you mentioned temperature control or things like that are a real issue. Because for example, in conventional MEMS devices, you want to apply one force in a particular spot, you can do it. When you go to nano, it's not so clear because electrical fields or forces are very difficult to confine to very small spots, and that requires a lot of issues. Another issue is forces related to quantum nature, like the Casimir effect. I can describe you better if you want later. These are forces that appear when you have parts with gaps between them of the order of 100 nanometer. And literally 100 nanometer or below. And then you have quantum forces that you do not control from outside, and you need to take into account when you design these devices. And that makes your life considerably more difficult.
Thank you.
I see a question.
Well,
Please.
you know, for our timing, I know you have a number of slides coming up. Why don't we just move forward, Dr. Lopez? Appreciate your responses to those questions. We'll have some time at the end as well. So
good,
go ahead.
Good. I'll try to move a little bit faster. Anyway,
okay,
this is one of the big directions where MEMS is going. Basically putting a lot of them together, packed really tight, and make them very, very small, because the smaller they are, the faster they are, and that allow you to have larger control over the signal that you want to manipulate. But the other big area is this intelligent microsystem. We want to have systems that they do things by themselves without us telling them from outside how to do this kind of thing. This is already tough to define because intelligence, there is no definition of intelligence, or a similar way to say is there are a lot of definitions of intelligence, but without getting into detail, this is what the kind of thing that we want the devices to do now by themselves. We want them to sense the environment, to have some idea of perception. Based on what they sense here, to do some action, they can move, they can change shape, they can do something, and then they can learn about this thing that happened here and use this learning to modify the perception again. You see, this is a kind of like a very crude definition of intelligence, but we are talking of structures that can sense, can do some action, and learn from what they did before. Nature does that spectacular. And this is one example of amoeba. There are no neurons in amoebas. Amoebas do not have brain. There are a lot of very small animals that do not have neurons, do not have brain, and they can survive very well. You see, this is an amoeba eating the inside of another cell. And it's an excellent example of a system, it's a biology system here, that can sense the environment, can do an action, and learn. See, this is different of what we do. You see, there are no neurons here. And this is called physical intelligence. Physical intelligence is, in a quick definition here, is to put inside some body, some structures, something, some level of intelligence. And I'm going to show you very simple examples for you to understand. And physical intelligence appears to be the most significant process of intelligence in the microscale. You see, for centimeter structure or larger like us, our intelligence is basically dominated by neurons, no? And I'm being very flexible in the definition here. For millimeter-sized devices or animals, there is some important component of physical intelligence, but here there is no brain. And And a lot of interesting things happen. No? Let me show you one macroscopic example of physical intelligence, a big one. Is this one. This is a Dutch artist that is very well known in creating this. He called this, I don't remember the name, it's like an animal beast of the sea, something like that. But these are machines, big macroscopic machines with well-defined mechanical parts that when the wind hits on them, they will move in a very precise way. There is no brain, there is no external control, and this is done very, very well just because the design of the physical components is done in the right way. There is another spectacular example that happened in the micrometer size scale, and it's this example of water bears or tardigrade. This is being studied with a lot of detail these days. These are 100 microns, between 100 and 200 microns aquatic creatures. They can survive extreme heat, radiation, vacuum. Basically, they can survive in conditions that any animal basically will die. No, this is from literally a research from 1 month ago from Daniel Cohen's group at Princeton. But there is a lot of interest to see how this animal can move, can interact with the environment. It's not clear that there is even a brain there. Then there has to be a lot of interesting things. And look, this is the size of the MEMS devices I showed you at the beginning, 100, 200 microns. But these animals survive and does a lot of interesting things just by itself. This is a picture from the bottom. The animal is talking on top of a piece of glass. And the size is 100 of microns, but the components, this is bio, no, don't get me wrong, but the components are well submicron. Engineers will dream of doing something like that is so independent, autonomous, and can literally gather energy from the environment without your input from outside. How can we do that? Let me give you a warning. We are not even close to do that. I'm going to show you some example of what are we doing to get to that level. And probably the technology is literally 5 or 10 years to get to that thing. No? Okay, what do we do? How we create this physical intelligence in microsystems? I will speed up because we are going a little bit slow. And the idea is to integrate some of the things that the state of the art, the cutting edge advances in optics, in mechanics, and in electronics to create this system who can use the optics to sense and to interact with the external world. You can have this Kirigami, and I'm going to show you now, these sub-micron or few microns devices that can change shape, and you can put electronics for them to communicate or eventually make decisions. I'm going to talk very quickly about each one of these 2 subjects. I will skip this, and I'll show you why it's cool to put it together. Let's see what is flat optics. You are all familiar with optics. And let's see, what is a lens, for example? You know how a piece of glass that we call lens work. You can see it here, the lens. The size of this lens is much thicker than the wavelengths of the light. But as you can see here, if you illuminate from one side with a very well collimated beam, very parallel beams, because the shape of the lens is not flat, you can literally introduce a delay to the beams here compared with here, and then you change this parallel propagation to a particular shape that will focus light. You see, when this beam got out of the lens, the rest of the beam is still here. And then when this beam is out of the lens, the other one is already here. That creates a bend, a curved profile who focus the light. In the last 10 years, there has been a lot of interest to do the same, but with nanofabrication technique. The idea is to replace lenses with materials that we can fabricate using the technology to create integrated circuits. There are a lot of things to develop, but it's a field that is advancing really fast. And you can replace this with something like this, flat, where each one of your structures introduce a different delay. I can talk with you later to see how this is done, but this exists today, and these are structured like that. You basically create a very thin film, flat now, it's not curved like this one, that when you illuminate, it will change the profile of light. That exists. That is a really hot field for research these days, because now you have the possibility to fabricate optics using the same processes that you use to fabricate MEMS. Exactly the same thing. And if you do that, you can literally put your optics on top of your MEMS devices without doing it by hand. And it is done today when you can create some optical system. And the other big advantage is these are flat. And in principle, that allow you to will allow you to replace all the big optical system that we have in today's best technology that consists of a large number of lenses, which make it big, macroscopic, and expensive for a variety of things. If we can replace all of these lenses with these nanofabricated films, basically there will be a new way, it will be a new way to fabricate systems that are much thinner, and we literally change the way that we do engineering today. You see, this is a spectacular telescopic system by a Chinese company doing cameras and zoom system for iPhones, for smartphones, sorry. And the limitation in any optical system today is the size of your lenses, because you need to make them by hand. You need to shape them in the way that you want to do it. And that is expensive and is not compatible with semiconductor processes. If you can do it the way that we are doing, and much more people, we are collaborating with Federico Capasso, which is probably the father of this field, one of the pioneers in this field. And what we are doing is putting on top of the MEMS that I showed you before, the optics. But now the optics, instead of being a big piece of glass, is another thin film fabricated with nanotechnology techniques. And then your whole system, your whole projector could be the thickness of a credit card. And that will literally is opening the field for a lot of applications. We'll speed up a little bit. If you can do that now, if your optics now is flat, it's just a film, a flexible film, you can put it on top of devices or material, sorry, that allow you to do origami or kirigami. I'm sure all of you are familiar with origami. Origami is the ancient Japanese art of folding papers. You can see here a little mice. Kirigami is origami with cuts. Remember from harakiri, kiri means cut. And that allows you to do much more interesting things than with just origami itself. The kind of thing that you can do is again, I wanted to show you some publications of some of my collaborators. These are literally 1-2 years old. There is a humongous interest in creating these flat films with cuts. And when you pull them or push them in some direction, they pop up in some 3D shape. You can see something by John Rogers at Northwestern. Here is for a very important group at Harvard. You literally start with a flat film, you make cuts, and then you ended up with very complicated three-dimensional structures that you cannot do otherwise. This is cool for a variety of reasons. I'll show you in a second. But if you follow what I was telling you before, these patterns are scale invariant. You see, if whatever you do in a piece of film, which is 10 meters big, it will work if you make it smaller. It will go, it's independent of the scale. Then you are starting to smell that we are going toward the development of a Moore's law for these nanomachines that could probably help us to do things that cannot be done before. This is a very simple example of something that we are doing. You take a piece of film, you may cut here, you, for example, heat it up and then became a propeller. Good luck to do this with conventional three-dimensional fabrication. It's almost impossible. And the other interesting thing is, if you make a structure like that, again, the dark lines here are cut in a film. If you apply the forces along this direction, it will tilt. If you apply forces in the other direction, it will bend. Then the same pattern that I make here can have different shapes if I apply forces in different directions. Then what you can do now is the same thing that we did before. Remember, we were putting these flat optics on top of MEMS. Now we are putting these little flat optics on top of this little Kirigami structure. Look at the sizes. These MEMS are the same I showed you at the beginning. 500 microns, half a millimeter. Now look at the sizes. This is literally 5 microns now. We are literally orders of magnitude smaller. And now we have the possibility to introduce this on flexible structures that you cannot do in this technology because it's rigid, and open up the possibility to do things that can change in shape when you introduce them from above. I'm almost done here. I wanted to show you them. I won't have too much time now. I mean, let me see. But I will skip this and I will go to this one because this is really, really wide. And this is, again, if you look at this paper, this is a paper from last year, and you will have a copy there. One big deal is to put all of this together and to make micron or nanometer size devices, very thin, but that so small that you can push them with light so fast that you can push them to reach a speed comparable to the speed of light. If you can take a little device, and I'm sorry we don't have time, but we can chat later if you send me an email. If you make a little device that where you put these flat optics, these super thin materials, you can make it very small, the size of a stamp, that when you hit it with a powerful laser, it can reach 20% of the speed of light. If you do that, you can send a sensor from our planet to Proxima Centauri b, which is the first exoplanet that we know that is beyond the solar system, in a time frame of 20 years. That's different. That's for you guys. For me, this kind of thing is something that now in a time scale of 20 years, we can send cameras to planets beyond the solar system. This is perhaps the next big thing in this area. As you see, as you know, there are a lot of interest in sending sensors. We just put a helicopter on Mars to send now sensors beyond the solar system is the next big thing. But what is interesting here is because of this technology, we can in 20 years send something before our solar system that nobody ever even thought about this before. I'm finishing here with this. I hope we have more time, but this is the two big directions where MEMS or NEMS are going. Putting a lot of things together, very small, very tight, or integrate them with optics and electronic to create these kind of devices. Of course, this doesn't exist. This is just a gift that I found online, but that literally show you what you could do in the next 10 years, probably, to create a structure that will be autonomous. And I'm sorry I didn't have time to talk about the role of electronics, but you can see how this combination of optics, mechanics, and electronics can generate a new class of devices that they weren't even a dream 5-10 years ago. Thank you very much. This is the list of collaborators. There are a lot of people from several years of work. But thanks, I appreciate your time. And if you have any questions, just send me an email later. I promise to reply. Thank you.
Dr. Lopez, thank you so much. I do have to share one comment you may not have seen there by one of our colleagues here in the MNT community, Dr. Matthias Pleil from the University of New Mexico, and he said, "You have blown my mind today." That is a good thing. And actually, we're gonna let Mike ask a question, and in the meantime, I'm gonna ask Renee to enable Dr. Pleil's microphone, so he might want to make some comments or ask a final question for us.
Dr. Lopez, so this origami, if I'm saying it correctly, you could have a pop-up MEMS, right? It could be sitting there and it could come up when it wanted to. And
one of the dreams will be you make something that is flat, it pop up, it goes away, measure something and send you the information, you see? And
I like it.
there are applications in electronics, for example. Some people would like to put electronics on top of this Kirigami, that when the electronics get too warm, too hot, the structure will change shape to allow cooling. And when it gets cold, it's recovered initial strengths and things like that. There are a lot of applications.
Wow. Let's invite Matt to come on.
Dr. Lopez, this was an awesome presentation. I'm so jazzed about it. You know, I learned a little bit about the MEMS optics stuff, the grading light valves and the DMDs and all of that. I used to work at Texas Instruments. So now seeing these surface patterns you put on there to manipulate the diffraction grading effects coming off of these micro mirrors, and then being able to put the cuts in and apply forces to change the shape. That's what's blowing my mind, is combining all of these cool mechanical things and you know, and applying it to these way out there ideas. But I think they're going to become commonplace in just a few years as things are accelerating.
Yeah, I hope so. There are a lot of interest.
Yeah, so it's really cool because, you know, I just started teaching a unit on MEMS in one of my sophomore engineering classes, and it's a mechanical engineering class. And I've had students ask, well, why are we learning about electronics and you know, and that sort of thing? But your talk just combined all of those things together and really
yes, you're welcome, and send me an email if you want. I can share more information, and if you want, I can give a class to your student. I've done that for people in mechanical engineering where we can go a little bit more technical, and that always helps. But yeah, Matt, I'll be glad to help.
I may take you up on that.
Please send me an email.
I want to interrupt for 1 second because we have to pay our bills. And paying our bills, we need to get your feedback from the participants. And Renee has put into the chat window a very, very short survey for our webinar. So we ask the participants before they go away, we'll stay on for a couple more minutes, to please click on that link and to and provide your feedback for today's webinar. We really appreciate that feedback, and it does help us to continuously improve our webinars. We will be continuing the series. This will be the last of the spring. We'll be continuing in the fall of 2021. So, but I just wanted to break in to make people aware of that. Open your chat window and go to that link to please provide feedback. Yeah. So I'm sure that Dr. Lopez is going to rate himself extremely high.
Bob, we have time for one more question, Dr.
Great,
Lopez.
go ahead.
If we can give it to you from our audience. We think about materials technology. You mentioned that silicon, of course, is the main driver, but have there been explorations of newer materials that could potentially work better, depending on the application, better than silicon? Maybe something that's better at changing shape, but you mentioned the origami type of things. What do you think? What about new materials for MEMS? What's your thinking?
That's a great question. The honest answer is for MEMS, silicon is very difficult to beat. I mean, as you know, silicon has been developed for 50 years.
Sure.
You can control the level of impurity 1 in billions. You can make it as conductive, very close to a metal. It's very tough, and the elastic properties, you know them very well. Where there is a tremendous need for new materials is in nano. In particular in nano, when you go from the big heavy MEMS, hundreds of micron, to very thin devices where the films are of the order of nanometers, 10 nanometers, sure, sometimes even below.
Sure.
The elastic properties start to change. And what do I mean by that? When you fabricate or design MEMS, hundreds of micron structure, the elastic constant of the materials are the same as the elastic constant as the Eiffel Tower, that the whatever humongous building, yeah, you want to think of, no?
Yeah.
Basically, elasticity is scale independent. When you go to the nano world, that breaks apart. and make the situation more complicated, because sometimes the elastic properties are a function of the size of your material, things like that. And that open up the door to new materials. But new materials for NEMS are a very, very interesting thing, in particular for Kirigami. That is a big need, because if you could have, as you imagine, when you have very thin materials and you start bending them up and down billions of times, you can start have some memory effect or cracks or things like that. And that's an area where the need for new materials is very important. Yeah, thanks, Mike. That's a good question.
You know, Bob, Dr. Lopez, thank you. Just an engaging, very informative presentation today. Bob, I'm going to turn back to you for a wrap up, and we're perfectly on time.
Of course, we're perfectly on time. When you're involved, we always are perfectly on time. I want to just again ask people to fill out that survey if they have not as of yet. I want to thank our webinar team, which we have adopted Dr. Plyle to help us today, and Dr. Lisicki, thank you for to help us out today. And of course, Dr. Lopez, you were invaluable today, and you did a fabulous job. When you blow Matt Plyle's mind, you've actually done something quite well. And of course, my greatest accolades go to our behind the scenes person, Renee Lindenberg, without which this webinar would not be possible. So thank you all. This officially concludes our webinar, and we're going to stop recording now. Thank you very much.